Hello and welcome to the latest webinar by BitGardener. My name is John Kowalski. I'm part of the marketing team here. I'd like to welcome you. Today we are talking dispersing and milling for energy storage. We have our Director of VMA Getzman USA Canada, Mr. Andy Stumer, going to present today. First off, if we are recording this, if you have and immediately following the presentation, you'll receive an automated link or automated email with that link. Feel free to listen later, share it with colleagues, wherever you like. There's some things you may want to take a screenshot of or screen grab. You're more than welcome to. Also, if you have any questions, please log them in the chat box located in the bottom right-hand corner of your screen. Time permitting, we will get to them. If for some reason we do run out of time, we will follow up directly with you to make sure your questions are answered. So with that, Andy, welcome. Glad to have you here again. And it's all yours, sir.
Thank you very much, John, and thanks everybody for joining us today. Maybe I met some of you last week at the battery conference or show up in Detroit, Michigan. We had a really nice booth there. But today, actually, we're going to cover some of the technology that we had on display there last week. And maybe later on, we have some time to answer some of your questions. So in a nutshell, we're just going to go and do a quick introduction of what we're trying to do. Then we're going to talk about the actual process, the dispersion and milling process overview, how we go about milling and dispersing. Then we're going to cover different types of equipment that is used to get us to the end goal. And then finally, we're going to close it out with sharing some of the lab capabilities that we have in Wallingford, Connecticut, at our sister company, Big USA, the additive manufacturer, as well as at VMA in Germany, where they make that equipment. As you can see already right there on that first slide, we cover everything from laboratory scale, pilot, all the way up to manufacturing for production requirements. This is only a snapshot. We have a lot more equipment choices. We also offer horizontal bead mills, so there's just not enough room on that one picture to show everything, but it just gives you an idea that we can fully scale with our technology. So basically, lithium-ion batteries, as everybody knows, and I was really impressed at what I have seen at the show last week in Detroit. It's just unbelievable how far along the industry has become over the last decade. I mean, it's unbelievable and where we are headed. So it's all good news. I think that all comes down to, from our standpoint, is using the right technology to really be able to mill the materials finer and more efficiently to give you a better solution. So that's really critical. And obviously, there's a lot of buzz around, these solid state technologies for improved performance and viability. So that is something we are also looking at. There's been discussion also on dry milling. Unfortunately, today, we don't focus on dry milling technology. So our magic dust, if you want to call it, that is really the wet milling of the slurries. So that's where our strength is really at, and not really the dry milling process. But it's something that we are actually actively looking at, and so maybe in the future we have some competitive solutions in that arena as well. Okay, so here's just an example of all the different materials that are being used today with our equipment, to mill it down and disperse it. So I don't need to read every one of them, but obviously you're familiar, lithium, polymers, we have carbon blacks, carbon graphites, nanotubes is a big one, detangle those with the use of a Cowles blade. We don't want to destroy them, obviously, and then we do a lot of work with carbon blacks and the basket mill approach, giving us really good results there. But there is many different uses for it. So you're familiar, the electrolyte in a battery, basically it is what it gives us the energy, and it's basically the ions flowing in between the anode and the cathode. And so they are most likely a liquid. So that's what we are working with our equipment, or it can be solid. So that's really critical there. So basically, just in a nutshell, our equipment really was born out of the coatings world. So all the paint makers and pigment development companies have really used this technology for many, many decades. And it has improved in about the last, I would say, 10 years, where we have really seen a spike and an increase in using the same type of technology for developing of these, electrolytes, and in reducing the particle size, very critical. I have to say, though, that a lot of these applications that we are seeing, especially for renewable energy and battery, require different types of materials. So our standard dispersers, call it an off-the-line product, is pretty much all stainless steel. 316 is great, but we are actually seeing that a lot of the requirements are changing, and there is a need for either the DLC coated parts, or we have seen a lot of ceramic requirements for silicon carbide or zirconium oxide. Actually, in some instances, we have seen where gold was required to develop these anode and cathode slurries, um, to make sure that there are no incompatibilities with the product and any type of performance issues that would result out of it. So the other challenge that always comes up, or question, I would say, is viscosity measurement directly during the process of dispersing and milling. So our material, our equipment actually has the ability to measure torque and read the torque directly. So we have on the standard machines, we have a calculated torque value from the frequency inverter, but we have often, I'll share it in a moment, something completely new. It's the TMS sensor, which is very cool, that actually does real-time viscosity measurement expressed in Newton meters on the shaft with its own sensor. So very, very important that we have accurate technology that allows you to really successfully upscale. So with that, um, here is the new Dispermat for fuels and battery applications. It's a Dispermat AERE and VLRE with the torque measurement system. That is actually a real measurement of the torque on the shaft and not a calculated value by the frequency inverter. As you can see that right here, that little um, wire that comes off and plugs right into, with the sensor that plugs right into the flange right there, right below the motor. That actually is where we take the measurement. And with that technology, we can get a very accurate reading of about 0.1 Newton meters. And that is actually displayed on our control panel. And in this case, we require a C control panel. We'll talk about that in a moment. But that is actually what gives us that reading, and it'll be a precise measurement and on display. And we can see in real time how a viscosity is changing. So there's also different types of sensor technologies that we can use for actually improving the torque range, what is sensitivity, if that is something that is required. Okay, next. So with the REA, so here's an example of how we process a cathode. So we have all of our raw materials. These are just examples, the PVDF, the NMP, and the carbon black that you can see right there going in. In this case here, we are looking at a 3-liter container, and that actually is that these machines can use different sizes, container sizes that are jacketed, and then we also have the torque measurement sensor, as well as this particular cover is actually a vacuum cover, so we can actually pull out the air and then have the ability to purge with either argon gas or nitrogen or any other inert gas that you may require to add into the mixing process. So here's an example of what we did with the same technology, but we actually used a basket mill in addition to the dissolver blade. And here we did a cathode slurry, and we used the CN20, which is basically laboratory scale disperser. And we pre-dispersed with the cow's blade for about 1 hour. And the starting point there were about 100 microns. And then after we pre-dispersed, we were able to get down to about 30 microns of particle size. Uh, and then after that point, we actually started to use a TML basket mill. We'll talk about that technology in a little bit. And we milled for about 3 hours, and we were able to reduce the particle size to 2 microns. So that's pretty impressive. You can see on the left that was during the pre-dispersion process, and on the right that was actually after we were done with the milling cycle using TML1 basket mill. So that was a laboratory scale um, process, and then we were using the Dispermat that I showed you earlier. Okay, so let's talk about the actual dispersion process and what we're trying to do. So by using a Dispermat with the cow's blade dissolver, you can see there are these building blocks, I call them, or these cubes. They are larger blocks. They're called agglomerates. This basically the particles are fused together. You know, with the carbon blacks, for example, you see under the microscope that the particle size is much larger than the primary particle size. So at that point, what we really need to do is separate these particles and put them back, ideally back into the primary particle state. So in order for us to accomplish that, we need to apply high shear forces that allows us to really mechanically break down the agglomerates by breaking up these binding forces, these invisible van der Waals forces that are holding these particles together, breaking up these binding forces and then separating them and turning these larger blocks into aggregates, which is basically same clusters, just smaller, less particles. And then when we want to go from the aggregate size down to the primary particle size, with the aggregate, we're talking anywhere between 10 to 30 microns of particle sizes at that point when we start the media milling process with beads is where we're then actually able to achieve that primary particle size. We cannot get from the agglomerates down to primary particles just by using a cow's blade. So that's why dispersing is actually always two parts. We have the pre-dispersion process, and then we have the fine grinding or fine dispersion or milling process that allows us to take the aggregates then to the primary particle size. And of course, uh, your formulators or the formulators in the room will know that you also need the right chemistry and right dispersants to keep then the particles in a suspended state once they have been properly separated. So our sister company, Big Additives, has some very good solutions there that will help you get there. I really like that slide. It kind of, visually shows what we're doing. So we first use the cow's blade. We are wetting our materials, and we are properly de-agglomerating. And when we have achieved the right particle size, 10 to 30 microns, which we call the aggregate level again, and then is actually when we start the milling process. And then finally, you can see the additives are in there that keep the particles in a suspended state because we don't want them to flocculate back together, which is also very critical. Doesn't matter how good the milling technology is, if the additive package doesn't keep up or is inferior, then it will all be worthless because then you'll have all these particles clumping back together again, flocculating back together again very quickly. So here is a lithium battery. Unfortunately, there is a video that is not working on the click share. So I cannot show you that, but what you will be seeing here is actually the basket mill in action. And so here we're actually dispersing a carbon black with the basket mill. And the additive that was used was Big USA additive for wetting, dispersing, and defoaming uh, agent Leponite RD. So if you go online, we have at the end of the presentation, we'll send you a link to our YouTube channel. And then there you can actually see a video of a basket mill in action, or you can actually come and visit us in the lab with your material, and then we can show you how that technology actually works. Okay, so this slide is really important to understanding kind of at what point the milling process starts. When are you done with using a cow's blade, a dissolver, and at what point are you starting to mill? So again, I mentioned earlier about 10 to 30 microns is kind of the threshold. And at that point, once you reach that aggregate size, is when you can start moving over to the bead mill. And obviously, there's different types of bead milling technologies. So the basket mill would be a vertical bead mill. And then we have also horizontal bead mills where you achieving much smaller particle size than with a basket mill. We have actually, in some instances, gone well below 50 microns, 50 nanometers with our horizontal bead mills and the nano kit. So that's especially when we're talking about separator coatings, where that is critical. Very, very small narrow particle size distribution and very small particles. Okay, so here you can see again, dispersing is a two-step process. Pre-dispersion, we use a dissolver. We have a different range of dispermats there, the SC for production, laboratory scale LC, CV, CN, and AE, which can also function as pilot units, depending on this container size and motor power that you require. What is really important is the actual tip speed. So we get a lot of questions about how fast should I be running my process? What's the RPM? And it always boils down to one thing. The RPMs are really only one part of the formula. It really matters the RPMs, also the diameter of the blade that you are using or the rotor as well. Obviously, if you're expressing that in meters per second, you divide everything by 60 after you multiply it with pi. I'll show you the formula in a moment, but you want to be anywhere between 18 to 25 meters per second when you're pre-dispersing. That's the optimum pre-dispersion window, as we call it. That's when you really put in the shear forces required to de-agglomerate. And when we are milling, we are running a little bit lower speeds, about 10 to 16 meters per second with the basket mill or a horizontal bead mill. So these are the optimum tip speed ranges for the pre-dispersion as well as the milling process. So very critical, very important, and probably the most important value when you're dialing in the optimum speed of your process. Okay. Other very important point is when you start out your pre-dispersion process and you have a batching process, so you have a certain container size. Question always comes up, how large should be the diameter of my blade? Well, so that really depends on a number of things. It depends on, of course, the viscosity of your material that you're trying to run. If you, for example, look over here on the right, there's a nice chart. And let's take, for example, I'm just going to pick the 1,000 milliliters. So it's a 1 liter or 1 quart container. You can see that we can use a blade diameter of about 30 millimeters all the way up to 70. So depending on my viscosity, if my viscosity is relatively low, like water, that's when I would be using a smaller blade to disperse. If I have higher viscosities, I would increase in blade diameter because what happens is if your material is really viscous, and we have seen almost pasty-like products, and you have a very small diameter blade, that would practically only sit in the middle of your container and spin, and nothing else would move around, that's outside of the diameter of the blade. So it's very important that as your viscosity increases, you would also go up in the diameter of your dispersion blade. The rule, the rule of thumb the rule of thumb is really about one third the diameter of your blade to vessel ratio. So that's how we actually start. If we have an optimum viscosity of about 3 to 5,000 centipoise. If we go larger, we increase the blade diameter. If our viscosity is lower, then we basically use a smaller diameter blade. And this concept fully scalable. It's also true for production scale volumes, just as it is for small batch volumes. Okay, so that's really critical to keep that in mind. The tape speed calculation, I think dialing in the correct speed is probably the most important piece of information. So you may want to write that down. Um, some pieces of equipment, like our higher end models, like the C technology, will actually display that information for you on the screen. But what we're doing here is we're calculating the peripheral speed of your blade, and that is calculate the RPMs of your unit times the pi, 3.14 times the diameter of your dispersion plate. So we talk about meters per second, so that means we divide everything by 60. Um, if that's what you want to look at. And it's important there to remember that the actual blade diameter, since let's say you're using a 50 millimeter blade, you would need to express that in meters. So a 50 millimeter blade would be calculated to 0.05 times, let's say, 5,000 RPMs, and then multiply that by 3.14, and then divide everything by 60. That would give you the actual tip speed of that diameter blade at the 5,000 RPMs. So again, when you're pre-dispersing, you want that value to be between 18 to 25 meters per second, and when you're milling, you want to be between 10 to 16. The formula is the same. It doesn't matter if you're pre-dispersing with the cow's blade, or if you're using a horizontal bead mill, a basket mill, or any other milling system where you have a spinning rotor or disc. The calculation will always be the same. But that's a very, very important formula. We use it every day, and to understand how fast are we actually running and processing our battery slurries. In this case, now we want to talk a little bit about the visual cue, the donut effect, which is actually named after the donut because it really looks like a donut. When you actually properly dial in your tip speed and you have the correct dispersion blade ratio to container ratio. So in this picture, it looks optimized. We are looking at a beautiful donut, and we can tell with confidence that the process looks good visually, and therefore we're probably going to achieve a very good pre-dispersion result. Um, so that is achieved by applying the shear forces from the machine through the blade. A cow's blade is the disc with those teeth. And on this particular picture, I'm actually missing the same graph, kind of like on the bottom of the blade, because the same dispersing action would take place also below the blade. So that's not shown here on the picture. But if you can visualize that, you're also shearing on the bottom. And that's where we're actually breaking up these van der Waals forces, and that's what leads to the separation of our agglomerates and turns them into the aggregate size. Okay, so in this case here, we have a dissolver batch. It was a picture that was done under standard coating, so it's not a battery slurry, just so you know, but the idea is exactly the same. We are looking here at an optimized dissolver batch. We can see the donut very well. Our tip speed, 21 meters per second, so we are optimum right there between 18 to 25 where we want to be. And we can see that we're putting in about 850 watts of energy. So that means we're doing a good job, really putting in the energy into our slurry, and we'll have a good tip speed. That means that the dissolver blade ratio looks good to the container. So that's all good. But there is going to be cases where you're going to see something like this. So what's happening here? We have 21 meters per second, but we're only putting in 320 watts of energy. So in this case, the viscosity of your material is very low. So it doesn't mean that you're not dispersing, but the donut would already automatically collapse as soon as it's being formed. So you don't see a donut. So that's the red flag right there, meaning, okay, I'm not putting in a lot of energy. So in order for you to achieve particle size reduction and the right amount of shearing to really break up the binding forces, you can look at your formula and maybe increase the viscosity somewhat, that you are able to put in more energy. So that's a viscosity issue right there. If you can't do that, okay, if you're not able to move anything around, adjust your formulation, then you're just going to have to be more patient in this case and disperse for longer periods, because it will take more time to break up the binding forces. Doesn't mean you're not dispersing. It's just you may not be as efficient as you want to be, especially when you go into a production environment where time is money. You really want to see a way that you can put energy in as much as possible, and then it will also give you a much quicker pre-dispersion result. Okay, and then we have scenarios where we have no donut effect at all. So we're running also at 21 meters per second. We're putting in 900 watts of energy, which actually means we're doing a good job dispersing, but I'm not seeing a donut. What's happening? This is a great example of no donut appearing because my viscosity is just so high that there is just no way for the donut to form. Doesn't mean I'm not dispersing. It's just it's outside of the optimum window where I would see a donut. So there is not really much you can do except also again tweak your formulation and maybe reduce the excuse me dry cough. But here you can actually maybe reduce the viscosity a little bit to have more flow of the material, and that will maybe give you a better looking donut. But it doesn't mean, even though you don't have the donut, that you are not able to disperse. Okay, so few things here that are critical when we're looking at the process, right, for pre-dispersion. The amount of time it takes to pre-disperse really depends on how we optimize our batch. So that can be anywhere from about 15 minutes to 1 hour. The donut effect, the visual cue, if we have the right viscosity of our mill base, we should see it. Tip speed, 18 to 25 meters per second, optimum. Geometric consideration, meaning the blade diameter ratio to our container, the right type of impeller disc. So depending on your material, your requirements, some customers have different blade designs. We do custom blades with an additional set of teeth. Also, the material that is used. So a lot of people cannot have stainless steel, so that will either be plated with DLC or we make full ceramic, zirconium oxide, or silicon carbide milling discs, or impeller discs. So it really depends on your choice of material. The amount of mill base. So we actually recommend about a 50% fill rate in your container, as low as 40%, but as high as 70%. You don't want to go more than that. Otherwise, you're going to see a spilling of your material, and that is not a good thing to have. If you go below 40%, then you're going to tend to set the blade at one height, and you can't really oscillate it. So sometimes when we want to optimize our dissolver batches, we want to be able to oscillate. But if you don't have any room, then you're not able to really move the blade around too much. So try to stick around 50% and go up to about 70 maximum. Um, the formulation, of course, is critical. Your type of material and the filler concentration. Um, Temperature, try to keep it as low as possible. When we are dispersing, and we saw before, 850 watts, 900 watts of energy, that means we're going to see a pretty rapid rise in our core temperature of our mill base. So we want to use jacketed vessels and a chilling system that allows us to really keep the temperature in check and keep it as low as possible, because it's going to go up regardless. It's a much not such a big issue when we are pre-dispersing, because we have limited amount of shear with the blade, but we really see this to be an issue when we are milling. We definitely need to have really good quality cooling and a good chiller setup when we are milling. Also, that the basket mills have cooling capability, and or your horizontal mills, obviously they need to have very good cooling capability, or you're going to run into a lot of issues, temperature related, and in some instances also hazardous. I just got a glass of water, so thank you. One moment. Okay.
And
Um,
if you have any questions, please log them in the chat box, and time permitting, we'll get to them.
okay. Can you still hear me?
Yes, loud and clear.
Okay. Okay, perfect. All right, and then additive packages are extremely important, right? We talked about that before. We want to be able to stabilize, defoam, um, and obviously doing the milling and dispersing process with a good dispersing agent helps us to get our 2 hour results much more efficiently. So that's really, really important. We have seen also with respect to foaming, just a little drop of a disperse of a entering foaming agent. It's like night and day. So really unbelievable technology, I have to say. And then the bead milling, right? That's our next step. Um, so let me go back one slide. Okay. So if we just stick, and we hear that sometimes from customers, is like, milling is difficult. We don't want to use a mill. There are speeds. The process is, more complicated, cleaning and everything. Can we just get there with the dissolver? And no, you can't really just use a dissolver on its own, because you're going to be limited amount of energy you're putting in. So therefore, probably 10 microns of particle size is where you're going to end up, unless you have really good quality, carbon black, for example, that had been previously already dispersed into the nano range. Then it's possible with the right additive package that you're able to separate the binding forces again and bring them back down. But normally, you would definitely need to mill because of that energy input issue with just a blade. Um, it's absolutely critical for any dispersion process. You can't just mix something with a mix or not disperse it and then think you can go straight into a bead mill. What's going to happen is you're going to have very large particle clusters that are going to be clogging your mill, and then you're going to have an issue, processing the material. You're going to have clogging. You're going to have to take the mill apart. So, not good. Always first disperse properly, and then when you reach the right particle size, again, 10 to 30 microns, that's when we start the media milling process. At that point, we're going to be able to put in a lot more energy. It will really help us get down into the nano range if we need to, with the right bead size. And we're really actually taking the aggregates and bringing them down to the primary particle size. That will give us a much better product characteristics, particle size, and better particle size distribution, which is so critical when we're looking at these slurries or separator coatings. So what's happening actually inside of a bead mill is pretty simple. You have a rotor, and then you have actually your beads. And if you look at this picture right there, you can see that as the beads collide, the particles actually get pushed away. And that force is responsible for separating the van der Waals. So that actually was causing the breaking up of the aggregates, not the actual crushing itself of the pigment. It's actually that separation of the binding forces. So it's almost like I always try to look at it this way, explain it very simple. When you were a kid and you sat in the bathtub and your mom gave you a rubber duck and you tried to catch the rubber duck between your hands, what happened? The rubber duck always got away, right? You're never really able to catch it if you try to, clap your hands. So that's exactly what's happening here. So that exact same thing is happening inside of a bead mill, but only at a much more rapid pace and much smaller particles. But the idea is the same. So that's what's causing the breaking up of the binding forces. And over time, we get smaller and smaller particles. But also, the smaller you get in particle size, you also will at some point have to readjust the size of your beads. So that means as I'm coming down in size, particle size progressively, eventually I'm going to have to adjust also my bead size to make the bead smaller to continue the milling process, right? So this is also a critical equation right here. You may want to write that down. It's what's critical is the kinetic energy that we're putting in to our milling process. So basically, it's the speed of our rotor, and obviously the weight of our beads is what basically is responsible for the amount of energy that we're putting into our slurry. So that comes up a lot. Is what how do I control that and what does it mean? What type of beads should we be using? So historically, when the old days, a lot of times, unfortunately, people were using glass beads to break up the binding forces. As you can see on this chart, that's really not such a good idea. Number one, glass is not really suitable for milling, um, hard materials because they are um, it will break. So if you look at the Wicker hardness of 400, a ceramic bead is 1150. So it's almost 3 times harder. And also it won't break up like a glass bead would, so you don't end up with shards in like inside of your slurry, giving you cross contamination issues. The other issue is that the wear of the beads, uh, if you're using glass, is very uneven. So that means over time you're going to have a lot of fines, and then you have to screen them out, and you're going to have very inconsistent milling results. So we highly recommend that when you're milling your slurries, that you always use zirconium oxide type beads, either cerium or yttrium stabilized, and that will give you much better milling results. Also, if you look at, they're almost 2.5 times as heavy as glass, so your kinetic energy is going to be a lot higher when you use ceramic type beads. Um, there's a picture here showing you kind of again illustrating what's happening in the bead mill. So as you see the beads come together, that shearing takes place right there in the corner, pushing away these particles. And that's what breaks up these binding forces. Um, Continually doing it, eventually you're going to end up with very fine particles. But again, you must adjust also the bead size as you get smaller to you also progressively use smaller beads. And we actually have nano kits with our basket mills or horizontal mills. You're able to use now beads 0.1 millimeter, and in some instances on the TML actually smaller than that. So these are extremely small beads. uh, I mentioned one thing, an issue there is the bead size, you know, gets smaller and smaller. It's going to be also more difficult to handle, right? So you're going to have to have really good cleaning procedure in place, screening procedure, but they're going to be everywhere really, and you're going to have to be really careful when you're taking your mills apart because these small beads are going to be everywhere, and it's going to be a little bit more challenging to clean as you go down in bead size. So here are some of the key parameters, particle size, bead size. Obviously, we talked about that, the specific weight, glass versus ceramic example, the bead volume. So each mill has like an optimum range. So there's not really one for each mill. So it really, you should, read the manual. There's a table in there of whatever milling system you use, and they give you a good optimum bead ratio. Again, screening of the beads is critical. Shape of the beads, you want them to be perfectly spherical or almost perfectly spherical. So be careful where you source your beads. There are some low cost bead manufacturers overseas that we know we have seen, and the samples look good. But when you buy your first batch, all of a sudden the milling performance goes down, and you're like, what's happening here? And then as you look at these beads under the microscope, you can see that they are not perfectly spherical anymore. They look more like footballs in an oval shape. So that's not good either. Again, critical value 10 to 16 meters per second when we are milling. That should be the speed of your milling disc or your rotor. Temperature of your product, the amount of cooling, critical again. Then the cycles, how often do I go through my milling chamber? The milling time, the residence time, it's the speed of my rotor. How long does my material stay inside of the milling chamber before I cycle it through? That could be a pump pressure adjustment or actually the speed of the rotor. So that's something that's also influencing the process. Mill-based viscosity, very critical. It needs to be a flowable material. If you have a paste that doesn't flow, the litmus test here is take a cup, have your material in a cup. If you turn it upside down, does the material flow out? If it doesn't flow out, it's very challenging to process the material with the conventional milling system, I would say. You definitely cannot do it with a basket mill. So you must have flowability of your product before you can process the material. If you do have a paste on horizontal milling systems, there is a plunger setup so that we will actually force your mill base through the milling chamber by pressure, and then we can bring back. But it's, I would say, a complicated process and more messy than it needs to be. So always try to see if you can adjust the viscosity of your mill base to make it flowable, and then we should have no problem processing the material. And then, of course, the type of bead mills. We talk a lot about basket milling and horizontal milling. So, depending on how small you want to go in particle size, our view is that if you want to stay somewhat above 500 nanometers and you're okay with the batch process, then there is no need to go with a horizontal media mill. The basket mill approach is a lot simpler. It's easier to work with. There are no O-rings or seals really. You have no leaking. Cleaning is a breeze on a horizontal mill. It's always a discussion. How do I best clean it? And then I have 20 parts sitting there, separation of the media from the milling chamber. All these things come into play. And then there's a lot more parts that can wear on a horizontal mill than on a basket mill. So customers today that do a lot of milling work, they're actually looking to move away from the horizontal media mills and move over to the basket mill approach because it's a lot more user friendly and cost effective. Cost effectiveness is very critical for us. So you can see on this picture, you're looking at a Dispermat AE, which is kind of our flagship machine for the lab space, also scalable to pilot and production, but you're looking at a lab model and it's fully modular. So we are able to accessorize the Dispermat any way we need to see it fit for the application. We can either add a rotor stator, we can add a vacuum system, a vertical bead mill called APS, we can add a scraper system, or we can add a basket mill system onto the same machine, which is really, really important because it can, save you a lot of money. You don't need to buy multiple machines, so everything can be done on one machine. The way that you go about changing these attachments is very simple. There is a shaft, and right below the motor, there is this clamping ring. I think Let me see if I can make this a little bigger. Okay, so you see there's a clamping ring right there below the motor on the top of my shaft, and you remove that, and then you turn this assembly about 180 degrees, and then you pull it out, and it's actually going to be very simple to pop in any of these other attachments, and then you just put the clamping ring back on. So now you have a fully, a full, push the wrong button here. Okay, back to normal. So you can actually then very quickly make that swap over, which is very user friendly. And without you having to spend all this money on buying multiple machines, you do everything on one machine as you just buy the attachment that you see that you need. This case, we have the lab battery slurry dissolver or high-speed mixer, some people call it, with the torque measurement system for really accurate real-time viscosity measurement. We have the vacuum option where we can add the argon or inert gas, nitrogen, whatever you need into the cover. We can go up to 20,000 RPMs on that particular unit. What's also interesting is with the C technology, we're not only able to run at a certain speed, but we can also run with a certain amount of energy. What that means, instead of saying I want to run 10,000 RPMs, I can say I want to run with 800 watts, 1,000 watts of energy. As your viscosity changes during the dispersing and milling process, the machine would automatically adjust the speed depending on our viscosity shift. So if our viscosity is increasing, but getting thicker, because increasing surface area, and we maintain 1,000 watts of energy, then our speed would decrease. If our viscosity gets lower, then our speed would increase if we're maintaining the 1,000 watts of energy. So that will also help us to scale to production very easily. And I can also pretty precisely calculate how much does it cost to produce a certain amount of product in the production environment in a certain amount of time if I'm running with constant power rather than constant speed. So planetary mixing is always a thing. It's always brought up, but really you're going to have particle size reduction limitations due to its design. Also, volume issue. Yeah, you always need quite a good number of volume of material. Here for lab scale, we can use very, very small amounts depending on the size of the blade, down to 0.05, so 5 milliliters of material, 50 milliliters of material is the smallest amount that we can process with our dissolver Dispermat technology. And the good news is we also have explosion-proof models. Everything is scalable all the way up to production. So very, very good and extremely quiet due to our direct drive motor technology. Then we have the vacuum dissolver right here. It's the VL with C. That actually also comes with a sweeper blade, container with cooling jackets. We got various sizes. Again, giving you optimum dispersing, high-speed dispersing and milling performance. Again, with the torque measurement sensor, a beautiful, effective piece of equipment. We have the new, and I'm going to go through a little bit quicker. We're going to get short on time, but we have the new CV3 Evo, perfect for lab, also perfect scalability as well as modularity with all the different attachments that we talked about before. Data extraction up to 20,000 RPMs. We have software. We can send everything over to Excel, so it's really, really cool. On the higher end model of the advanced model, we actually have a scale that's integrated. You can see the measurements of your materials on the display. CN line, kind of our medium range dissolver, fully capable, perfect. That this will give us the ability to scale it and also go all the way up to production. Here is a pilot scale model of our CN line, perfect for electrolyte development. Then that's the AE model. It's our flagship machine. Again, lab scale, C technology. We can go all the way up to 31 gallons with the pilot, and then larger in the manufacturing with the manufacturing machines. Again, all the upscaling capabilities, data storing capabilities, and power control options. So very, very effective piece of machinery. Again, same model, except larger scale for pilot. Horizontal mills, we got the SL on the left, which is our lab scale with the nano kit, and then we have the RS for production scale on the right, depending on the volume. So with the RS horizontal mill, we can produce about 1,000 liters an hour in continuous mode or pass through. So we have the RS5 all the way up to 250 liters from 25 to the RS30 up from 151,000 liters an hour, which is pretty large and same effectiveness as on the smaller ones on the smaller SL. Okay, then we have the dissolver technology, the SC, which is basically production scale disperser, high-speed mixer with vacuum capability. The modularity, same thing as on the small one. You can add on a basket milling system or a vacuum system or a scraper system, depending on your requirements. But again, very cool because I buy one machine for all my dispersing and milling needs, and I can do up to 2,000 liters of material. And again, explosion-proof models are available. So it's perfect for a plant that's looking to expand, or you have limited space for milling system, as well as separate dispersers. That's where the quick change systems come in. You see here, we have it set up as a dissolver on the left, and then on the right, it's the same machine using a basket mill. So also with ceramic options where you can add a rotor stator. There's many different options on how you can configure it. We would be using a transport trolley to do that. A changeover will probably take about less than 3 minutes. So a very quick change and very simple to perform that. It takes one person and you can, within 3 minutes, move from a dissolver over to a basket mill. Vacuum dissolver, large scale, really great because we can put in a good amount of energy. We get better wetting and dispersing effect. Air bubbles are kind of like little air mattresses in your slurry. By removing these, we don't have, those cushions in there. So I'm actually have improved homogenization and I don't have any foaming by removing the air. So that means I can also transfer from one vessel very quickly to another vessel when I'm done milling or dispersing by removing the air bubbles. And I have the ability on the larger scale also to add nitrogen or any type of inert gas into my cover with a port, allowing me to create either a blanket or purge it with those gases. Then we have the really cool machine for production. It's the TM version. Very popular because it already integrates a basket mill. So basically, you're dispersing first. When you're ready to do milling, you just push a button on the control panel. The basket comes down, and now you're milling without having to move containers around. No need to move a basket from the trolley or up to the machine. So this is actually already a fully integrated solution where we're dispersing and milling on one system. Really, really cool machine. Here you just can see it here, pre-dispersing first, and then using the basket mill for your fine grinding. Also very easy to clean and not really a lot of wear parts. So that's the other beauty. The operators really love it, that they don't have to deal with all these parts and seals as they would on a horizontal mill setup. Here is an example of an actual production environment where there are two TM1000s being installed. You can see a very large container, 2,500 liters back there. The dissolver discs have not been installed yet, but you can see right there, they are leaning against the blue drum. This is fully raised on the left and collapsed on the right. They're the exact same machine, except one has the container right there, and one on the right would actually what it would look like when it's actually running that the machine, the stand would actually be lowered with the motor to actually go into the vessel. These are workhorses. They run 24/7. Here is a close-up of our basket mill. So that screw right there is where we actually put the beads into the beads. And then we have a pumping wheel right in there that would actually suck the slurry into our basket. That's where the beads are at the milling disc. And we have very effective cooling efficiency by running a channel. You see these bars holding the basket. So there is one for cooling in through one of these bars, and on the other side, cooling out. And then the third one behind, you can see it a little bit, kind of in the middle of the picture. Behind the bar on the right is actually where we measure the temperature through that bar inside of our basket. So very, very nice design with the couch blade on the bottom for optimum removal of the mill base through the screen on the bottom of our basket, then push it back around to the top where then that pumping wheel will suck it back in for optimum rotation of our slurry through the basket mill. Here is an APS system. We call it the vertical bead mill, processing material in a laboratory environment only because this is not really scalable. So we have two containers. We have a container on top and then one on the bottom. In the container in the top, we do actually the processing, the milling of our material. You can see there are the beads in there, the milling disc. And then there is a cover that comes over. Once we're done milling, we actually plug in an air hose into a socket in the cover. We pressurize the container, and then we remove a drain plug on the bottom. And there's a screen actually that holds the beads inside of the top container. And then with air pressure, we're purging the material right below into the container below. Again, very efficient milling. It's really good, but it's not really, unfortunately, scalable because of the bead handling issue at very large volumes. You can actually add 100% bead loading. So if you have 500 milliliters of slurry, I can add 500 milliliters of beads, giving you very efficient milling performance. Just quickly, control panels. On the left, you see the C technology with your speed, your energy, your torque value, your temperature, tip speed, and timer function, and fully programmable with cutoff values so that you can set temperature limits or torque limits and all those things to make sure that your process is running safely. On the right, we have more of a production scale display control panel. Very simple, very easy, but also very effective. Doesn't get dirty, or if it does, it's very easy to clean. Laboratory scaling in Germany right here at VMA. So if you have a sister company or you are in Germany, please visit us with your materials. We can process it. We can demonstrate the efficiency of our basket mill system, horizontal mills, and then help you scale that to a production scale process. We have a lab space in Connecticut where we have some of this equipment, where we can also demo that to you with your materials and do proof of concept trials and basically show you the differences between the different milling and dispersing technologies. At Big USA is where the lab is located. We have the milling, the additive package experts for battery and fuel cell. I just put this slide in there to give you a little idea of what they can bring to the table. But they have more in-depth presentations on the correct type of additive package that would be suitable for your application. So the Wallingford Lab, great facility. We call it a battery additive development center. We leverage the synergies between our additives team and the hardware team, which is us, to make sure that if you pick our equipment, that you also have the ability to, leverage, all that knowledge and giving you the best possible product performance with our equipment. Scaling up is very important. We'll help you with that from laboratory scale up to production scale. And then we can use it as a showroom for our equipment And also, if you want to come in and learn more about just the technology itself, what we did today, be our guest. We can set that up. So with that, we hit exactly the 1 hour mark. Thank you
Yeah.
so much for your time today.
Yeah, good timing, Andy. And thank you, everyone, for joining us. Like I said, you'll get an automated email with a link to this recording shortly after we close out here. If you have any questions later today, tomorrow, next week, you can simply hit reply to any of the marketing messages you get, and we will route them to Andy and his team to get you the answers you need. Thank you so much, and we look forward to seeing you on future BitGardener dispersion webinars. Thank you, and thank you again, Andy, for your expertise.
Thank you. Have a good day, everyone.